Hello and welcome back to TCP and You. My name is Chris Gabrielson and this is part 4, the final part of this training. This is going to be the tips and tricks as well as a very quick wrap up at the end to cover what it was that we learned throughout this entire saga. I'm going to go ahead and kick it off by talking a little bit more in detail on iPerf, which we covered in the previous section. iPerf I found to be an extremely valuable tool in order to prove out whether or not the network really is or is not the issue. Most customers out there have either a Windows or Mac, and this being just a simple kind of command line executable, it doesn't require a lot of overhead from an installation perspective, and it's also fairly well known in the industry. A lot of customers use it already, and so I think it's just an extremely kind of neat tool to play around with. Now, if you're unfamiliar with the way iPerf works, you essentially need to install it on between one and two devices. One is going to act as a client, the other is going to act as a server. And I say one to two because, as we pointed out earlier, there are some public iPerf servers where if you just wanted to install it as a client somewhere in order to test some sort of speed connectivity out to the internet while having the ability to modify your settings, that's something you could do. But otherwise, it's just a client and server application, and I like it because, given there's no graphics or anything else, it's pretty much, sky's the limit. But it's also important to point out that you will be limited by the CPU and NIC of the devices involved. So if you're generating a whole bunch of traffic with iPerf, keep in mind you will see the CPU of that particular device spike because something's got to generate all this kind of garbage data in order to just send out as part of TCP. Now, if you go to iperf.fr, it is I guess, a French tool, but obviously everything's in English. This is the website, and you can see here, you can look at the binaries, various servers. There's a couple different flavors of iPerf as well. There's iPerf 2, and at the time of this recording, there's iPerf 3. I'd recommend you stick with iPerf 3 for the time being. And just download it for whatever your application is. So we can see here, it's a little hard to see, but there's Windows, Android, iPhones, Apple, Mac OS. It's there for Linux. So pretty much anything and everything you can think of, there is a client for it. And the one application can act as both a client and a server. There's not one dedicated for the other. Now, assuming you have this installed on your PC, how do you use it? Well, it's pretty simple. If you are operating as the server, you just need this iperf3.exe-s, and you would run that on a command line within whatever directory this is installed in. So if you're a Windows user and you were to put this on your desktop, you pull up a command line, do cd desktop with a capital D, and that'll bring you to your desktop. And then you can just run iperf3.exe -s, and it'll now run it as a server, and it'll wait for some client to connect. There's really not a whole lot you can do on the server. On the client, though, I do include a few examples of what we could do. So to start off, you could simply say iperf3.exe-c for client, and then put in the IP address of your server. And this is just a good initial test to make sure your server is reachable and everything works the way it should. The default setting is to run, I believe it's just a quick TCP transfer of just, there's no data, no files, it's just kind of garbage made up data, but it lasts for about 10 seconds. So that's a good start. But then the next one, we could also tell it, if we don't want it to use TCP, we can have it start with UDP. So iperf3 client server IP -u implies use UDP instead of TCP. The -b says try to hit this bandwidth. Because remember, TCP has that windowing mechanism. UDP doesn't care. It's connectionless. It will send traffic as fast as it possibly can. You just need to tell it how fast you want it to go. So this command here will send UDP traffic at a rate of 1 gig per second. It'll just start blasting it out, send it to the network, and let the network take care of it. The next option down, we saw this a little bit in the previous slide. So once again, client, server IP, and here I'm modifying the TCP window and I'm setting it to 1 meg. And we could see here that sizes, whenever we're talking about any sort of size, be it bandwidth, window size, or any of the other settings, you can use these letters. So K, M, and G for kilobits, megabits, or gigabits. So 1K would be, the same as just 1,000 if you didn't put in any values. But you could play around with the window size as we saw in the previous set of slides. And then the final one is how we can increase the time and or reverse the direction. So if you do an iperf dash dash help or just a single dash with an H, you'll see all of the different options available to you. But again, if you wanted this to run for an extended period of time, the default is 10 seconds, but you could do dash T, make it run 60 seconds, maybe even more, have it run a few minutes, hours, whatever. All of that is configurable, and by reversing the direction, that'll change it where instead of having the client send the server or server send the client, you can essentially adjust the direction, or you can even make it bidirectional. So highly flexible tool when it comes to being able to test the network or test the device that you're working with in order to get something going. Uh, Now, what exactly can we use some of these for? Well, for something like UDP, I like to use the UDP option in order to prove the network can handle the volume. A lot of times customers might say, "Oh no, this switch it can't transmit more than 200 megs per second." And I go, "Well, if it's a gig link, then it should be able to hit line rate. It should be able to go a gig a second. So let's send UDP, which doesn't care about packet loss or anything else, and let's just send UDP at a rate of 1 gig per second and see, does the receiver get approximately 1 gig per second? And if so, how much loss was there?" This is a great way to prove to a customer that if they have a 1 gig link, it'll transmit 1 gig a second. Or if there's something like a policer or shaper in the path, UDP traffic will be impacted by that just like TCP will, and it should be fairly evident whether or not the traffic is being rate limited in some way. Now, the network, again, right, it'll treat TCP UDP equally. So if you could hit, 900 or more megabits per second on a 1 gig link with UDP, and it'll also give you a printout telling you whether or not there's loss, then that means the same should exist for TCP. And if you're not getting 900 megs per second with TCP, but you are getting it with UDP and it's loss free, well, that indicates that we have either a client or server issue. Because again, network does not care. TCP, UDP, packet's a packet, right? Network is going to send it. So if you're able to get those higher speeds in UDP, then the fact that you don't get them on TCP means it must be one of those settings that's keeping it down arbitrarily. Now, from a TCP perspective, as I showed you in the part 3, near the tail end of part 3, you can adjust your window size in order to demonstrate to a customer how, without changing anything in the network, you can get drastically different speeds by changing some of the settings within the TCP application itself. And this is something I like to kind of play around with, where I could show a customer, hey, your network, without changing a single thing, if I do a window size of 100K, I only get a few megs. If I bump it up to 10 meg, which is about as big as it'll typically go, then I'll start getting hundreds of megs of TCP. And this is very useful, again, if you're doing an analysis for a customer and you have no packet loss and there's nothing wrong that you could tell with the network, the speeds just appear slow, then this might be a good option for you, where you could use TCP, adjust the window size. I believe the default window size is only 64. So keep in mind, even just default iperf client, not going to get a whole lot of speed. You will need to modify that TCP window size. And if you do, and you can bump it up and you get great speeds between your client and server, but whatever application they're using just doesn't see the same speed, well, that proves out this is not a network problem. Because if iperf can get the speeds they expect, but their application cannot, Well, the network doesn't really care what the application is unless they have some sort of QoS or other policy that's explicitly looking for it. But if the answer is no, there's nothing in the path that would otherwise treat that traffic differently, well, then chances are you're looking at a client or application issue. And then the last one I have here is for the public iPerf servers. Again, we talked about them briefly, but if you want to play around with public servers in order to see even how things like window size or everything else plays a role, a lot of customers like to use something like speed test, some sort of online speed test in order to test their performance. I like iPerf because I can get it down to a single TCP socket and I can change around settings so that I can get a very kind of specific test and control some of the variables in order to see, is this truly a network issue or maybe a speed test issue or something else. And this is, again, something I use quite often when trying to troubleshoot. You've got a few options. The ones I use, given I'm here in the US, are the Hurricane Electric iPerfs, but there's also this eenet.ee, kind of a weird domain name, but it works. And if you go to the iperf.fr website, there's a list of all the public servers. Keep in mind, some of them do have non-default ports, meaning you will need to specify a unique TCP port number to run the test, otherwise iPerf won't connect. So highly encourage you to play around with this tool, even if it's just on your desktop, because in enough time, there's a very good chance some customer will be using it as part of their testing suite, and it'll definitely help you to understand how it works. And if you know how it works, you could show them whether or not their test may or may not be valid. The next tip and trick that I want to show you guys is some of the benefits when it comes to using simultaneous captures. More specifically, how we could filter the captures out so that the first and last packet is identical in both. And what I mean by that is, and I'll start off with a more kind of simple example. Typically, when we're looking at these simultaneous packet captures, we have time going down. Customer's going to go to one device, they're going to start the packet capture, so that'll be starting here closer to time 0. Then they walk over or they log into the other device and they start the other capture. Then once both captures are started, even though they had slightly different starting times, then they do their test. So somewhere here in the middle was our transfer, and then at the bottom they say, okay, now the transfer is done. They stop one capture and then they take a couple seconds and stop the other. What we want for the easiest analysis is to make it so that the beginning and ending packet in both of these is the exact same thing. Now, if you have something like the three-way handshake and you can export it out, export out just the flow, that is one option. But maybe you didn't have the three-way handshake, or you just want to highlight part of the packet capture or something similar. Maybe you just want to get all the TCP flows within a particular time. This next section is going to be for you. So if I want to export out only the traffic that is common to both these captures, again, maybe I don't know what the socket is going to be, I just want it to be like for like, what can I do? Well, the first thing I like to do is to identify a packet that is common to both captures. And one of the easiest ways I could do that is by just picking a frame and looking at the IP ID, or the IP identification. This is a value that exists in every single packet. If it has an IPv4 header, then it has an IP ID. And if you right click this, it'll give you the option to apply it as a filter. And when you do, you'll get the IP ID over here. And once I have this, I'll write down, okay, what packet number is this? So if it's a packet capture of 1,000,000 packets and this ID 396D, if this is number 1000, then I write down 1000. It's at this point, though, I usually get some pushback. People might say, well, Chris, my packet capture, it doesn't have an IP ID, or they're all 0. What can I do to find something in common? And for that, a lot of times I might just find an actual data packet, find the payload, and filter on that instead. More than likely, the payload for any individual packet will be unique. So if your IP ID is all 0, because they all have one, it just may not actually be set, you could go to your TCP header. We can see a snippet of it here. I have the TCP payload. When you click that, it'll highlight all the hex in binary down here. And then if you right click this, it'll bring up this menu. You mouse over apply as filter and then click selected. This will now put the tcp.payload equals, and it'll be a big long string with all, in this case, 821 bytes worth of raw data. And now you will be able to filter out that one packet, and you could do it on the other side. So I have my two packet captures using either IP or the TCP payload. I identify which packets are common to both because I was writing down the number. And I could see here at this time, whatever IP I chose, here it was packet number 527. Over on the other capture, it was 13881. I then do the exact same process for the very last packet in the capture that is common to both of them. So in the first capture was packet 881535, and in the one over here was 712444. Knowing those two ranges, I can now export them out, and if I do it successfully, then that means both of my captures will start and end with the exact same packets. The way I export this out, knowing the exact packet numbers and what number they were in each capture. So for capture number 2, we're dealing with 527 through 712444, and in capture number 1, we're dealing with 13881 through 881535. So that means when I go to Wireshark, I can go to File, Export Specified Packets, and then put in a range. And it could be captured or displayed depending on if you're trying to filter out a specific TCP flow. Maybe you want to do displayed. If you want all the TCP traffic, then maybe you might do captured. But I want to put in those two numbers that I know are common to both captures. And I'm going to do this twice, once for capture 1 and again for capture 2. When it's done, I can now open up the captures that I just exported. And I can see, okay, capture 1 right here, using the same source and destination, if it had a total size of 432,825, and if capture 2, which has the exact same source or exact same starting and ending packet, if it's the same size, then I know without even going any further, without even applying a single filter, there is no packet loss between these two captures. I don't even need to look at TCP. There might be retransmissions, but the retransmissions were not between these two capture points. Every packet that is in the first one is in the second. They match up. There's no loss between where these two were collected. Otherwise, if the numbers are different, so if I'm expecting 432,825 and I get a number that is different between those, then that is an indicator that yes, there must be packet loss between these two endpoints. Now I could start maybe diving into some of the things that we learned about TCP in order to figure out what or where. Alright, so this last section was pretty quick. Let's go ahead and do some final thoughts and wrap-ups for this training as a whole. And I want to cover what exactly did we learn. Let's talk about it kind of verbally here. To start, in one of our first sections, we talked about where can we collect packet captures and what tools are going to be good tools to use and which ones are bad. Remember, things like Wireshark and physical spans are ideal. EPC is a very poor choice when it comes to troubleshooting TCP slowness. Do not use embedded packet captures to troubleshoot TCP throughput issues. We also learned in this section a little bit about TCP dump. If you're looking at a packet capture and you see very large packets or very small packets that you wouldn't think would normally fit on a network, well, chances are whatever device you're capturing on is getting the data before it actually gets broken up by the NIC and put on the network. That's where physical spans are going to be best, because now we're seeing exactly what the network saw. Additionally, in our second bullet here, always collect two captures. Always, very important concept. One of these captures needs to be fast, the other needs to be slow. And the reason for this is because slowness is relative. What is fast for one customer might be slow for another. And because it is relative, we need to have a way to kind of do a stare and compare to see, okay, this is what this particular customer thinks is fast, and this is what they think is slow. Once I have my two captures, it's very easy to figure out, okay, what is different between these two. And that's where I'm looking at things like, what is the latency? Is the latency the same or is it different? What does the window size look like? Is it the same or is it different? What does the packet loss look like? Is it the same or is it different? Once I have one of those outliers identified, I could start chasing it down and hopefully figure out what the problem is. And when it comes to figuring that out, the third bullet here covers some of the tools available to us. So we learned how to graph throughput within Wireshark in order to have a very good visual of what is happening to this TCP flow over time. A customer may say something like, oh, TCP is running at 300 megs a second. But it's not till you actually look at the graph in Wireshark and you could see, well, is that sustained 100% of the time? Or is the traffic maybe a little bit more variable than that? And how much does it vary? So we talked about the throughput graphs. We also talked about window size graphing within Wireshark. Also very important. Remember, the window size is telling the destination how much they can send before it must be acknowledged. Just because the window size is a certain value does not mean the other side is obligated to fill it. That obligation or lack thereof is the congestion window. And that is not something that exists within Wireshark. That's something that you just need to know about, and hopefully this training has given you some knowledge on. Whenever we're using these fast versus slow captures, it should be very easy with these tools in order to figure out what is the delta. We also learned that if we know the latency, window size, and connection speed of our client, we can calculate the maximum theoretical throughput of a TCP flow. And this is very useful for figuring out what should a client get in terms of theoretical speeds. And not everything is perfect, so we'll typically be a little bit lower, but it may be a good way to tell that if you have a scenario where your customer has no packet loss, no retransmissions, no duplicate acts, but they still don't get the speeds they expect, we could figure out what is the maximum theoretical throughput and potentially show that to them, which may indicate they need to change a setting on their client or on the application. And then finally, using some of our tips and tricks, as well as tools like iPerf and a few others, we figured out if there might be a way to tell whether or not the network is truly at fault or if it's a network or application issue. The final thought that I would leave you here is, generally speaking, the only thing the network can introduce is packet loss. If you see retransmissions and duplicate acts, there's a very good chance that those are introduced by the network somewhere. But if you do not see retransmissions and you do not see duplicate acts, the vast majority of the time, it is not the network that is at fault. Instead, if the customer is not getting the TCP speeds that they expect and there's no packet loss, it is highly unlikely that the network is introducing something. At that point, the only thing it could change really is latency and maybe the window sizes. But it's very unlikely the network is at fault, and it's likely some sort of setting on the client or server. And that's where we could use tools like iPerf to manually test out things like changing the window size or changing some sort of setting to see, does this truly work if we take this customer's application away. And that concludes TCP and U. I hope you found this training useful. I would love to hear from you if it was something that you learned something about, or if it helped to solve your case. That would be a great win for me. Otherwise, feel free to take a look at some of my other trainings on my box folder. And if you're interested in something that I did not cover and would like to see me do a training, feel free to reach out. I'm always looking for new ideas and working to get better stuff out there to hopefully have you solve some cases quicker. Thank you for your time, and until next time, have a great day.